Okay, so this is part 2 of the lecture on convergence tests. So I'll begin part 2 with the absolute convergence test. So let me write this out. So absolute convergence test says that if an is a sequence and if this infinite sum converges, the infinite sum of the absolute value of each an converges, then the infinite sum of the ans also converges. Okay, so simple enough. So remember, here we're taking the absolute value, and here we're just summing the original sequence. So example, I gave a top hat question yesterday, and it asked if you could use the integral test to determine whether or not this infinite sum converges. It's cos n divided by n squared. And the answer is no, because it doesn't satisfy the conditions of the integral test. In particular, the ans are not positive. They're sometimes positive, sometimes negative. So that's one reason why you can't use it. But you could use the absolute convergence test. Actually, for this, you're going to need to use both the absolute convergence test and the comparison test. So you need to use 2 tests to solve this. So it's a pretty good example. So we have this sequence, and these terms are sometimes positive, sometimes negative. So let's use the absolute convergence test. So we're going to take the absolute value. So look at sorry, this should be a 1. I'm dividing by n squared, so I can't start at 0. So this is just cos n over n squared. I mean, n squared is already positive, so it doesn't matter if I include the absolute value in the denominator. Now, the question is, does this series converge? If it does, then the absolute convergence test will tell us that this series also converges. So how could we do this? So maybe pause it now before I reveal the answer and think about it. Okay, welcome back. I hope you paused it. So this is an example where we could, yeah, it's comparison. We should compare it. We should use comparison test, and what we can compare it to is 1 over n squared. So cos n divided by n squared. So this is, first of all, it's always non-negative, and it's always less than or equal to 1 over n squared, right? Because cos n is always between -1 and 1. So this is always less than or equal to n squared, to 1 over n squared. Therefore, since n equals the infinite sum from n equals 1 to infinity of 1 over n squared converges, so does this sum. Or I should say, so does, maybe, let me say it like this. Since this converges, so does this by comparison test. Did you see this? I think so. So we know that this converges, but then by the absolute convergence test, we get that this converges. So this implies this converges. And And that's how it's done. Just like that. So remember, if you have any questions about anything I'm saying in the video, just leave a comment and I'll try to respond in a reasonable amount of time. So, okay. So I think that does it for the absolute convergence test. So let's, so what's the next one? Ratio, I think? So yeah, let's do the ratio. Basically, ratio test. I'm not sure if I should actually write out the test or not, because I'm not sure if it's useful. Maybe I shouldn't be. So we have a sequence AN. The ratio test says that if the limit, so suppose the limit as n goes to infinity of the ratios of AN plus 1 over AN is equal to L. Then, well, so I guess there's an issue here already. If AN is 0, this doesn't make sense. So you should only consider sequences which, well, you need to be able to divide it. So like eventually for a big enough n, AN can't be 0, but let me just brush that aside. So suppose this limit is equal to L, then there are three possibilities. Either 1, L is less than 1. 2, L is bigger than 1. 3, L is equal to 1. So suppose, so if L is less than 1, then what the ratio test tells us that. So let me put a 1 here. So in the case 1, the ratio test tells us that this infinite sum converges. Now in the case 2, the ratio test tells us that the infinite sum diverges. Now let me just pause here first for a moment and just mention something. If you ever forget which one is which, just you can think about it and figure it out. So if L is less than 1, so there's two possibilities. So we're looking at the two possibilities: L is less than 1, L is bigger than 1. If you remember that one of them converges and one of them doesn't, one of them implies convergence and one of them doesn't, then just think about it logically. If this limit is equal to L, which is less than 1, then it tells you that the terms are getting smaller and smaller, right? But or they're eventually getting smaller and smaller. But if the limit is bigger than 1, then it tells you that eventually the terms are getting bigger and bigger. Now, in order for a series to converge, you need the terms to be eventually going to 0. So they can't be eventually getting bigger and bigger. They need to be eventually, well, they need to be going to 0 eventually. So between these two, only this one makes sense for convergence. So this one, it definitely, if the terms are getting bigger and bigger, it can't converge. There's no way. So that's just sort of like a sanity check, kind of. I don't know if that makes sense to you, but you should think about it more. 3. So in the case 3, the ratio test doesn't tell us anything. We don't know anything. So yeah, it's totally useless. totally useless in the case that L is equal to 1. So what's an example of this? Case, simple example. Let an be 1 over n squared. 1 over n factorial. Then this limit, so this thing right here, so this is equal to limit as n goes to infinity of n plus 1 factorial divided by n factorial. Actually, maybe this isn't a great example. Stand by. Oh, wait. I think I messed it up. No, sorry, it is a good example. All right, I messed up the computation. I went too quickly. It's equal to n factorial divided by n plus 1 factorial, this limit. And this is equal to the limit as n goes to infinity of 1 over n plus 1. Which is, this is equal to 0. So by ratio test, this series converges. Recall that 0 factorial is equal to 1. 0 factorial is defined to be 1. So by the ratio test, this series converges. Actually, fun fact, this is equal to e, the number e. Now, this is just a fun fact. It's not, nothing I wrote here implies that it's equal to e, but just maybe you think it's interesting. Where are we at? What time? Oh, 12 minutes. Okay, so let me do last one. Alternating series, but pause it now anyway. It's maybe a lot. Also, or maybe it's not. I don't know. Alternating series. I want to make sure I say it exactly right. Okay, so suppose that an is a positive sequence. So this is bigger than 0 for all n. And it's strictly decreasing. So, and an is bigger than an plus 1, also for all n. And in addition, suppose that the limit of the sequence is 0. Then this series converges. So, what's a good example of this? Why the most simple example is the one they give. So I don't know if it's, maybe I'll just give that anyway. So, example. This converges. So you should think about how to apply the alternating series test to this example. Note that I'm not really being strict about whether or not I start the index from 0 or 1. Here I wrote it starts from 0, here it starts from 1. But the point is that it doesn't actually matter what number you start at, because you could always change a finite number of terms in the sequence, and it doesn't affect convergence. It'll affect what the sum is if it converges, but it doesn't actually affect convergence. So I can start at 10, 100, a million, a billion, doesn't matter. All that matters is that I have to go to infinity.